Now, we'll start to shift away from the celestial sphere, and let's talk about the angular size of an object. Now, what the heck do I mean by angular size? Take a pencil, take your writing utensil, and hold it a centimeter away from your nose right now. How big is your pencil? Pretty large. Now, fully extend your arm out, hold that same object a distance further away from your face, and now it appears smaller. Right? This is what I mean by angular size. What angle does that object take in your field of view? So here formally we'll say the angular size of an object, which we'll label with a delta, you can measure in degrees or radians. Right? Let's talk about these units. Right? 1 degree, or it can be measured as 60 arc minutes, or 3,600 arc seconds. These are new angular units that we're trying to measure now. When it comes to measuring positions of stars on the celestial sphere, we're going to have to use measurements sometimes that are much smaller than even these arc seconds. Going to another unit, we'd say 360 degrees is equal to 2 pi radians. Why the heck do we even care about these radian things? Is because it's what we'd say is a natural property of angular measurements. If you ever talk to scientists, astronomers, physicists, all we want to do is measure radians. But as a society, we started off with degrees, and we use the arc minutes and arc seconds because of the small displacements that stars will have in their angular positions. All right? With that off to the side, let's finally define formally this angular size. And it is the ratio of the object size, which is a lowercase d, over the distance to the object, a capital D. So here's pictorially, right? This will be your field of vision. How big is the angular size of the object? Well, you measure how far away the object is. And when it comes to stars, we'll know that how far away the object is always a much bigger value than how big the object is. So coming back to our equation, we'd say the diameter of that object is just equal to the distance to it times its angular size, if that was measured in radians. If you have it in degrees, well, it's a simple multiplication. You'd say the diameter of the object is equal to the distance times the angular size in degrees times pi divided by 180. So let's do this in practice, right? Alpha Centauri, it is 4.37 light years away, our nearest stellar neighbor. Now imagine that I was able to cut that distance in half, right? What would happen to the angular size of Alpha Centauri if it was suddenly 2.185 light years away? Now pause the video, take for a moment, look at the previous equation, calculate this out. And you come back after you pause, we'll work this out together. So, equation. The size, how big that object is equal to its angular size times the distance to it. Rewriting that around, we say, look, the angular size is proportional to 1 over the distance to the object. I don't care about the size of Alpha Centauri because it's not changing in this problem. So we can just say angular size is proportional to 1 over the distance to it. Now let's calculate the new angular size. We denote it with a prime here. The new angular size of Alpha Centauri is proportional to 1 over half the distance. We half the distance to Alpha Centauri now. So 1 divided by 1/2, a half in the denominator is equivalent to a 2 in the numerator. So we say that the angular size has now doubled. When Alpha Centauri was half as close, it will be twice as big in our picture. Another problem that astronomers like to tackle is how big something is. Imagine trying to measure the circumference of the Earth. You can't exactly grab a string and wrap it around the circumference of the planet. So here was an ancient astronomer's method to solve the problem. This was a man named Eratosthenes, who was born in 276 BCE. Eratosthenes knew of a well in Syene, and it had a peculiar property that at a certain time of the year, there was a well in Syene, and you could see directly into the bottom of this well. And what Eratosthenes logicked out is, hey, at that time of the year, the Earth is lined up with the sun such that the sun's rays are going straight into the well, all the way to the bottom, not casting a shadow. And that was the crucial step. Eratosthenes, working all the way in Alexandria, would look at the shadow cast by the sun on the building he lived in on that same day. And he'd say, hey, look at this. He determined that the sun was forming a 7-degree angle relative from Alexandria to Syene. Rays are coming in, Alexandria is at this 7-degree angle. So, all Eratosthenes realized he needed was the circumference of the Earth. If he could measure this distance and knowing this angle, he could calculate how big the Earth was. How do you get this measurement? So first I'll tell you the values. Eratosthenes, he figured out that the two cities were about 925 kilometers apart. He got this by asking merchants to keep track of the number of footsteps they'd make as they traveled between the cities. And he paid people sometimes to even travel the distance, get them to come back home and tell them how many steps they'd taken along the way. And with that estimate, he was able to calculate the circumference of the Earth. And he calculated the Earth had to be 46,250 kilometers in its circumference, which, if we compare it to our actual values, is closer to 40,000 kilometers. Not too bad for a person just asking people on the streets, how many steps did you take?